Hello everyone, welcome back to our channel. So till now in the second semester mathematics for triple E stream we have covered two important modules. Okay, those two modules with detailed explanation along with all the problems. We have solved everything in that two modules. It is available in this channel itself. Okay, in this playlist we are continuing with module 3 now. Our first module that is vector algebra, and second module that is a vector space and linear transformations. Both of them we have completed. So today we are going to start with module 3, that is Laplace transform. Okay, so this is one very important module with respect to examination point of view, and it is a lengthiest module. Okay, out of all the modules this is the most lengthiest module with many concepts and the problems and all. There are many problems. Okay, so you should be practicing a lot of problems from this module because the problems are in a huge number, but I have taken some important questions from each topic. Okay, all the different kind of questions for keeping in mind the examination point of view that I'm going to solve. Okay, so again in this module also we are having two chapters. One is, as in the title suggests, Laplace transform, and second chapter is related to the inverse Laplace transform. Okay, yeah. So this was about the complete intro of this module. Let us start with the definition part now. So let us see first the definition of Laplace transform. Definition: let f of t be a function of t defined for all the positive value of t. Then the Laplace transform of f of t, that is L of f of t. Laplace transform is denoted by L. Okay, it is denoted by L of f of t is equal to integration from 0 to infinity e to the power minus st into f of t dt. Okay, with respect to t we are doing the Laplace transform. Okay, so this is the basic definition of Laplace transform here, and this is in this way the Laplace transform is represented. That is L of f of t is equal to integration from 0 to infinity e to the power minus st f of t dt. Okay, where S is the parameter which may be real or complex. Okay, it suggests that the parameter S it does not have any restrictions to have. It should be a real value. It could be any complex value as well with some complex conjugates. Okay, the value of S is real or complex when this definite integral is evaluated between the limits from t equal to 0 to infinity as suggested here. We will be left with the function of S only. Okay. So when we after doing the integration from the limits from 0 to infinity, we will be left with the term S only, and we shall denote it by f of S. Okay, after doing the integration we would be getting the function in terms of S variable. Okay, so that's why we should be denoting the Laplace transform of f of t. We could be writing it is equal to f of S. Okay, that only we have written it here, that is f of S is the representation, or we could be even writing f dash of S. Okay, so you keep this in picture like this. You could be representing, that is L of f of t is equal to integration from 0 to infinity e to the power minus st f of t dt is equal to f of S. Okay, because after doing the integration part we would be left with only S terms, so that's why the function we would be getting only in terms of S. Okay, so this was about the complete definition. Now let us see to the existence part, that is how it is existed. The Laplace transform of f of t, that is integration from 0 to infinity e power minus st f of t dt, exists for all the values of S greater than 0. Okay, it should be strictly positive in order to be existed. That is, it should the values of S should be greater than 0, and f of t is continuous. Also the limit tending from t to infinity, Laplace transform of f of t is a finite integral. Okay, so this was about the existence part. Next is uniqueness. If the Laplace transform of the given function exists, it is uniquely determined. Okay, hence we may say that the inverse of the given Laplace transform is essentially unique. Okay, so it is a unique term with one unique solution. We don't have any number of sets of solution. Whatever solution we do for after applying the Laplace transform as well as the inverse Laplace transform, one unique solution we would be getting. Okay, in particular, if we have two continuous functions which have some transform, they are completely identical to each other. Okay, they are completely interrelated to each other whenever they are having two set of functions. Okay, so this was about the uniqueness. Now we have some of the very important Laplace transform of some of the elementary functions. Okay, those whatever I tell right from now, all those things are very important with concern to the problems while we are solving for Laplace transform. Okay, so let us see some of the Laplace transform of some of the elementary functions. Okay, some functions should be there generally. For that we should be, for that what is its Laplace transform, we should be knowing it. Okay, in order to solve problems, these things are very essential. Let us discuss that one by one now. Transform of elementary functions. First one, we have Laplace transform of 1. Okay, Laplace transform of 1 is equal to 1 by s. Okay, so this is the standard way of representing L of 1, that is 1 by s. So by definition of Laplace transform, we have L of f of t is equal to, this we are proving now, 0 to infinity e power minus st f of t dt, right? So here a value of f of t, in place of f of t we have 1, right? So f of t is equal to 1. So L of 1 is equal to, in place of f of t I have written 1 e to the power minus st dt. So if you multiply it with 1, we would be getting e to the power minus st only. So you take its integration of this is e to the power minus st divided by minus s, and the limits are from 0 to infinity. So apply upper limit minus lower limit condition and take minus 1 by s common, and upper limit e to the power minus s into infinity minus of e to the power minus s into 0. Okay, infinity into anything is infinity only, so we would be getting e to the power minus infinity minus e to the power 0. So anything to the power 0 is 1, and e to the power minus infinity is equal to 0. So minus 1 by s into 0 minus 1, that is minus 1 by s into minus 1. So minus minus is minus into minus is plus, so we would be left with finally 1 by s. Okay, so hence we have proved that Laplace transform of 1 is equal to 1 by s by putting the definition of Laplace transform. So this was the first transform of. Next we have very important one, that is Laplace transform of t to the power n. Okay, what we would be getting? We would be getting Laplace transform of t to the power n is equal to n factorial divided by s to the power n plus 1. Okay, so this is the Laplace transform of t to the power n. Whenever we have the terms such as t, t square, t cube, or it could be represented in general as t to the power n. So you will be getting n factorial divided by s to the power n plus 1. So let us prove this now. Again, by definition of Laplace transform, here f of t, in place of f of t what we have, t to the power n. So substitute that. Okay, so here I have substituted it. L of t to the power n is equal to integration from 0 to infinity e to the power minus st t power n dt. So name it as equation 1. Okay, now do some of the substitution methods. Then where e to the power st is there, right, put st is equal to p. So you would be getting t is equal to p by s. So if you take its differentiation dt, we would be getting 1 by s, you take it common. So differentiation of p is dp. So substitute this in equation 1 what you have taken. So limits would be changing from t. For t is equal to 0, p would be equal to 0. And for t is equal to infinity, p would be equal to infinity only. Okay. So the limits now for p is again from 0 to infinity only. So now whatever we have substituted, write it as it is, that is in place of st you write it as p. So in place of t to the power n we had, so t is equal to p by s, right? So p by s to the power n and 1 by s dp. In place of dt we should be writing 1 by s into dp. Okay, so now 1 by s to the power n plus 1 is common here. If you observe here, this is p by s whole to the power n. This could be written as p to the power n divided by s to the power n, right? This here. So here s to the power n, and here we have s to the power 1. So bases are same, the powers get added, right? So that's why 1 by s to the power n plus 1, you take it common outside. Then do the remaining integration, that is e to the power minus p power n dp. Okay. So this is of the form. If you observe here, we have one gamma function here which you might not be knowing. This is one new note to you guys which you need to be knowing. That is one gamma function, that is gamma of n plus 1 is equal to integration from 0 to infinity e to the power minus x into x power n dx. Okay. So here if you see this and this, these are same. Only the variable p is changed. Okay. So we can be applying this gamma function here and writing this as 1 by s to the power n plus 1 into gamma of n plus 1, okay, according to this condition. So this would be equal to gamma of n plus 1, okay, and now 1 by s to the power n plus 1, we should be writing this gamma of n plus 1 in terms of n factorial, because gamma of n plus 1 is equal to n times of gamma of n, okay. So similarly for n times we are having the values from 0 to infinity, so that's why we could be writing in general as n factorial into gamma of 1. So we know that gamma of 1 is equal to 1, so substitute that n factorial into 1, so we would be getting our final answer as n factorial divided by s to the power n plus 1, okay, hence proved. So this was the second transform. Next, the third one, Laplace transform of e to the power at, okay. Laplace transform of e to the power at, what we are getting, 1 divided by s minus a, where a is any constant value which should be varying from 0 to infinity, okay. Yeah. By definition, again apply the definition. In place of f of t we have e to the power at, okay. Put that e to the power at, so here powers are same, so it would be getting added up. Minus of e to the power minus of s minus a t dt. So here take its integration. So minus of s minus a is a coefficient of t, that would be getting divided, and apply the upper limit and lower limit condition, okay. Minus 1 by s minus a, you take it common outside, so upper limit minus lower limit to apply, solve it, and we would be getting our answer as finally 1 divided by s minus a, okay. Check the steps and check for the answer, okay. So this is the answer we got, hence proved, okay. This was the third one. Next, fourth one, Laplace transform of sine at, okay. This is very important one. The Laplace transform of sine at, again the value of a would be varying from 0 to infinity, okay. It is a constant, that its Laplace transform is given as a divided by s square plus a square, okay. So let us prove this also now. By definition of Laplace transform, here f of t is equal to sine at. So it is written as Laplace transform of sine at is equal to 0 to infinity e to the power minus st sine at dt. So this is of the form, we have one standard formula for this, that is integration of e to the power at sine bt dt, okay, that is given by e to the power at divided by a square plus b square into a sine bt minus b cos bt, okay. This is the general formula. According to that, in place of a we have minus s, and in place of b we have a, okay. So according to that only substitute the values, that is e to the power at, in place of a it is minus s, and in place of a, again here we have a square, so minus s the whole square, and in place of b we have a, okay. Then do the necessary substitutions here, minus s sine at minus a cos of minus s into t, okay. Then apply the limits from 0 to infinity, okay. And then check here, 1 by s square plus a square is common, you take it outside. So we are left with e to the power minus s into infinity upper limit, okay, into minus s sine infinity minus a cos of minus s into infinity. In place of t you substitute infinity, and solve it, and we would be getting finally our answer as, if you simplify it, we would be getting as a divided by a square s square plus a square, okay, hence proved. So let us see the next one now. Laplace transform of cos at, okay. We have discussed with sin at, right? Now we have one more cos at. Its Laplace transform is given by s divided by s square plus a square, okay. The numerator part would be getting changed. In place of sin we had a divided by s square plus a square, and for cos we are having s divided by s square plus a square, okay. Again prove that. In place of f of t you write cos at. Again for this we have one more general standard formula, that is integration of e to the power at cos bt dt is given by e to the power at divided by a square plus b square into a cos bt plus b sin bt, okay. Substitute that, okay. Substitute the value of whatever, in place of a we have minus s, and in place of b we have a. Again do the necessary substitution, solve it like this by solving for upper limit and lower limit, check the steps clearly, okay. Then substitute the values, and we will be getting finally as s divided by s square plus a square, okay. So these were the 5 important elementary functions. So we have one more, 2 more very important functions. Those are hyperbolic functions, okay. Very important hyperbolic functions that we are going to see now, okay. Trigonometric hyperbolic formula, okay. The hyperbolic functions, it is represented by there are two standard formulas for that. One is sin h of x, okay, that is given by e to the power x minus e to the power minus x divided by 2. And similarly we have cos h of x is equal to e to the power x plus e to the power minus x divided by 2. Okay, these two are called trigonometric hyperbolic formulas, okay, with the standard formulas here. So in place of x here we are having now the sixth transform elementary function, that is sin h of at. Okay, in place of x we have at. Okay, so Laplace transform of this we would be getting it as a divided by s square minus a square. Okay, let us see that how we are getting. So here by definition of Laplace transform, write it here f of t, in place of f of t what we are having sin h at. So in place of here x what we are having at, so substitute that is e to the power at minus e to the power minus at divided by 2. Okay, this you should be putting it in place of f of t here while proving it. So put it, and here we can see that 1 by 2 is common, you take it outside. So we are left with e to the power minus st into e to the power at minus e to the power minus at into dt. Okay, multiply separately these two and these two and split the integration, okay, with the minus sign. Okay, here take common term, add the powers in both the cases and do the separate integrations step by step. Observe it how I have done it. Okay, and here again 1 divided by minus 1 divided by s minus a, you can take it common from both these terms. Okay, so we are left with only the numerator part and take the integration here. Okay, apply the upper limit and lower limits and solve. Okay, see the steps here, step by step I have solved it. Each step you observe carefully. Here I have just taken the LCM, cross multiplied, and I have done it. And here s would be getting cancelled here. Okay, and here we are left with a plus a, that is equal to 2a. So already we have here a 1 by 2, so there 2 would be getting cancelled, and we would be left with a divided by s square minus a square. Okay, so this is for sin h at. Similarly we have for cos hyperbolic function, that is cos h at. Okay, and it is given by s divided by s square plus a square. Okay, where a is the value of any constant value, it should be varying from 0 to infinity. Okay, again apply the same condition here. In place of h x we have here at, so here accordingly substitute the value of f of t here. Okay, and solve it in the same way how we have solved for sine, right? In the same way solve it for cos as well. Check out the steps clearly. Okay, each step you observe carefully. Very easy, simple integration you should be doing it. Okay, then apply the upper limit and lower limit conditions, and we would be getting it as, after solving here, s divided by s square plus a square. Okay, hence proof. So yeah, that's all guys for this video. These were some of the important Laplace transform of some elementary functions, standard functions, where we are going to use these in the problems as well. Some 7 we have discussed. Those 7 are very important ones. Some more are there that while seeing through the problems we are going to discuss. One thing is there, we are going to solve a lot of problems in this module. Okay, there are a lot of problems because the variety of problems are a bit more in this module. So I would be dealing with all kinds of problems in order to make you clear. Okay, yeah. So this was about the first video. We have covered this first video with some of the very important introduction part. So hope you understood something. So if you understood something, you please show your love by liking this video, subscribe to our channel, and stay updated for the next video. Okay, so we are going to see with the properties of Laplace transform from the next video. Okay, yeah, so that's all. Thank you.